I hope it is visible. Okay, fine. Okay, so start with the basic definition of continuity. So, let D be a non-empty subset of real lines. Okay, so D is non-empty I'm taking, and F is a function from D to R, so it's a real valued function. Let's take a point, let's C is an element of D, then F Okay, I think now I'm so this is an equivalent definition of continuity. There is one more equivalent definition, which says that which says that instead of this, we have like another equivalent way to say that for each epsilon greater than 0, there exists a delta greater than 0, such that f of c plus h minus f of c is less than epsilon whenever mod of h is less than delta and c plus h is belong to the domain. Okay, so this is another way to say f is continuous at c if for any epsilon greater than 0, depends on the choice of epsilon, there will exist a delta greater than 0, such that f of c plus h minus f of c, this difference should be less than epsilon whenever mod of h is less than delta. Okay, so all these are like, here our neighborhood is nothing but the epsilon neighborhood. In the first definition, we say that there should, for each neighborhood of f of c, we'll have a neighborhood of c. Okay, so what's going on this all this definition? So for each epsilon neighborhood of f of c, we are getting a delta neighborhood of c. Okay. Okay. So now you can clearly see that some very simple fact. So let's say if c is an isolated point. Okay. So let me make some remark. Let C belongs to D is an isolated point. Which means what? Can you tell me what do you mean by isolated point? So C is an element of D and is an isolated point. What is the meaning of it? So there exists a neighborhood which will contain, there exists a neighborhood of C which will contain the element C only. Okay. So other way to say that, then there exists a delta greater than 0 such that that neighborhood, delta neighborhood of C contain the element C only. Okay, there is no other element than C. Okay, so what will happen then? So if we look at the definition, we have f of x minus f of c is less than epsilon whenever x belongs to nc delta intersection d. Now if we choose whatever epsilon we have, if we choose the same delta, then this x is nothing but c, and then fx minus f of c will be 0, and because epsilon is greater than 0, so obviously this inequality will hold, correct? So that means if c is an isolated point, function is definitely continuous at that point. Okay, because by default, so therefore you can say that f is continuous at c belongs to d, okay, if it is an isolated point. Okay. Okay. Let's see. So from there you can, yeah. Yeah, I should write that way. Yeah, correct. Because it's an element of D. Okay. Otherwise, like, so that's what I am going to say. Like, take the set of all natural number. So there in that set, like 1 is an isolated point, but 1 in general not an isolated point. Okay. So yes, we should mention that D intersection this. Thank you. So this is the thing. Like as we said that set of, if we consider D as a set of all natural number, then any function from the set of natural number to R will be a continuous function. And we know that a function from the set of natural number to the real line is a sequence. Okay. So the sequence is a continuous function. Okay, now next, let's say D is a limit point of, sorry, C is a limit point. So remark 2, let C belongs to D intersection D dash. So it's in derived set. So it's a limit point of the sets D. Okay. Then this is a equivalence. You can prove this statement. Then F is continuous at C if and only limit x tends to C, fx equals to f of C. So this is a general definition people use, but this definition only works if we have C as a limit point. Okay. So if you have a limit point, the limit x tends to C, fx should be equals to f of C. Okay. We are not proving this. It's a very simple fact. You can prove it. Okay. Now let's discuss a little bit. Most of the cases will take D as an interval in a real line. Okay. So because that's easy to handle in the other sense, or easy to visualize basically all these things. Okay. Next, let's say, so if we have to just spend little more time on epsilon delta definition. So be very careful. What we have, we are saying that f is continuous at C. Okay. If for any epsilon greater than 0, there exists a delta greater than 0 such that fx minus f of C is less than epsilon whenever n C delta intersection D, whenever x is in this set. Okay. Now fixed a epsilon. Okay, so fix an epsilon. So I will change a point C to some other point C dash. Okay. Now fix this epsilon greater than 0. Let's say because we have, so what will happen? Let's take now another point C dash. Okay, C dash be another point of the set D. Okay. So same epsilon, we have other point C dash belongs to D. And assume that f is continuous at the same point C dash. Okay. Then this delta might not work for the same C dash. Okay. So you need, so then, and assume, obviously, assume that f is continuous at C dash. Okay. Then it might possible that there exists an element x in the neighborhood intersection D, delta neighborhood of C dash, such that fx minus f of C is greater than epsilon, greater than or equals to epsilon. Okay. That means what is it? So, but f is continuous at the point. So you need a different delta. Might be a smallest one, smaller one, a smaller delta than that delta which works for C. Okay. So the important thing is that this delta not only depend on the choice of epsilon, it's also depend on the choice of point. Okay. So what is the thing I want to say that if is continuous at C or at any point, it is important okay, so I'm not writing. It's important to note that this delta, whatever epsilon we have, this delta depends on both epsilon as well as the point. Okay. So now, okay, let me. Okay, anyway, we'll say that a function is continuous on a set if it is continuous at each point of the set. Okay. Now let's take all such delta. So we are considering for fixed epsilon greater than 0. We are considering in delta, so we are setting new delta, which is infimum of all epsilon comma c such that c belongs to D. So fix epsilon and assume that, so assume that f is continuous on D. That means it is continuous at each point of D. Okay. And for that particular epsilon, let's say this delta epsilon c means for this delta, that definition will work. That fx minus f of c less than epsilon whenever nc delta intersection D will work. Now, if we take this infimum, and obviously this set has bounded, so infimum will exist. So this delta is greater than equals to 0. Okay. So that means you might not find a delta, suitable delta, which will work for all the element of C. Okay. So because this, or there is a possibility that, so there is a possibility that this delta might become 0. Okay. So other way to say, there might not exist a delta for which which will work for all the C. Okay. So other way to say, there might not exist any delta for which will work for all C. Okay. So now but there might be a possibility that there might exist another delta, one delta exists which will work for all C. Okay. I mean, there might be a function for which this will work. Okay. So now we'll make it as a definition. So there are some function for which this delta will work. Okay. So here we have the definition of uniform continuity. So because it will work uniformly for all value of C, so that's why we have this name, that uniform continuity. What is that? So we are saying, so uniform continuity. The definition is that let D is a subset of R. Okay, so non-empty subset of R. Let f from D to R be a function. Then f is said to be uniformly continuous on D. We'll say that f is uniformly continuous on D if for any epsilon greater than 0 there exists, so I'm using short notation, there exists a delta greater than 0 such that mod of f of x minus f of y is less than epsilon whenever mod of x minus y is less than delta, and obviously x, y are elements of D. Okay. So if we have two elements x and y in the set D which is satisfying this inequality, then it must satisfy that f of x minus f of c less than epsilon. Okay. So now we can see that if a function is uniformly continuous, it should be continuous at each point of D. Because take whatever c, this delta will work for each value of c. Okay, other important thing is that it might there is a possibility that for a function this inequality holds for one epsilon but might not hold for other epsilon. So that's why it's for any epsilon greater than 0. That means it should hold for all epsilon. Whatever epsilon you have, for that particular epsilon, you will have a choice. We will have a delta which will depend on the choice of epsilon for which this inequality will work. Okay. So what's an example? Okay, let's see an example of a uniformly continuous function. And also an example which is only continuous but not uniformly continuous. Okay. Okay, so I'm not writing, but it's very clear that a uniformly continuous function is a continuous function. Let's take fx is 1 by x. X belongs to 1 to infinity. So we'll prove that this function is uniformly continuous. Okay. Then obviously it will be a continuous function. Okay. So let epsilon be given. So any epsilon be given, arbitrary epsilon we have. So suppose we have to calculate f of x minus f of y. We need to show that this is less than epsilon, something like that. Okay. So because we need to get a delta for which this will work. So now if we calculate fx minus f of y, so we'll see that it will be 1 by x minus 1 by y. So it will be y minus x by x into y. Okay, so mod is there, but it's all positive. So fine. So we need to make it less than epsilon. Okay. So now look over here, because x, y both are greater than or equals to 1. So 1 by x of y should be less than or equals to 1, correct? So both x, y are greater than or equals to 1 implies that 1 by xy is less than or equals to 1. Correct? So now choose delta. So let's take delta equals to epsilon, because epsilon is given. It's known to you. Okay. So epsilon, let's say I give you an epsilon. You need to find a delta which will satisfy the definition. So let if delta equals to epsilon. Okay. Then what will happen? Then this term y minus x by y minus x, it's obviously, like, let's say I choose, okay, why is it? Yeah, here. Then let's assume that we have this is less than delta, which is epsilon. Implies y minus x by y by x. Okay. So will be obviously less than epsilon, because 1 by y minus x is less than 1. Okay. So if you multiply both sides, it will be less than epsilon. Okay. Okay. So there is, yeah, that's all. So that will going to work. So this is therefore f is a uniformly continuous function. You see that whatever epsilon we have, we'll choose delta equals to epsilon. You can choose a delta which is less than epsilon. That's also going to work. Then if we have x and y, if the difference between x and y is less than epsilon, absolute difference between them is less than epsilon, then absolute difference between fx and f of y will be less than epsilon as well. Okay. So this means that f is uniformly continuous. So therefore, f is uniformly continuous. Obviously, when we are saying a function is uniformly continuous, we are saying that it's a uniformly continuous on a set. Okay, so we should write on 1 comma infinity. But look over here. For continuity, we say that a function is continuous at a point, but here we are not using that term. We are not saying that a function is uniformly continuous at a point. So uniform continuity is a property of a set. Okay, in that sense, but continuity is a property of a point in that other way to say. Okay, so like you cannot say that a function is uniformly continuous at a point, but you can say that a function is continuous at a point. Correct. Okay. The other important thing is that you should say that it's uniformly continuous on a set. Why? Because if you consider the same function, let fx equals to 1 by x. Now x is defined on this set. Instead of 1 to infinity, we are saying that fx is 1 by x. Take the domain from 0 to infinity. So we'll define function over here. Okay. So you can prove that. I'm not doing it, but like using epsilon delta definition, you can prove that this function is not uniformly continuous on 0 to infinity, but this function is continuous on 0 to infinity. So this is an example. Then f is not uniformly continuous on 0 to infinity, but f is continuous on 0 to infinity. Okay, you can use epsilon delta definition and try to solve this problem, but we'll go one by one. We'll have new tools which will help us to solve this problem very easily. Okay, instead of going through this tedious work of finding delta, we'll have some theorem that we'll use as a tool to solve this problem. Okay, so anyway, so that's why it's very important to say that a function is uniformly continuous on a particular set. Okay. Should not say that's just a uniformly continuous function. Now, okay, we have learned that if a function is uniformly continuous on a set, it should be continuous function. Okay. What about the other way? It's not true. But can we characterize some sets where the function uniformly continuous function is a continuous function? Okay. So here is a simple theorem we're going to prove right now. So it says that so let A from closed and bounded interval AB to R be a continuous function. Okay. Then f is uniformly continuous. Uniformly continuous on AB, closed and bounded interval AB. If we have a function from closed and bounded interval to R, which is continuous, then it is uniformly continuous on AB. Okay, let's try to prove this. We prove this by the method of proving by contradiction. Okay, so let's assume that f is not continuous. Okay, suppose on contrary, f is not uniformly continuous on AB. Okay. Then what can we say? What is the implication of this statement? That if is not uniformly continuous on AB. What is the implication of it? So there exists an epsilon for which we will not going to find a delta. Okay. So then there exists, let's say epsilon naught greater than 0 such that for all delta greater than 0 we have x, y less than delta and f of x minus f of y is greater than equals to, let's say, so we'll have a pair of elements x and y such that x minus y is less than delta, but fx minus f of y is greater than equals to epsilon naught. Okay. So depends on the whatever delta we have. So now you see that let's take so other would say thus for each n belongs to set of all natural numbers, there exists a pair of sequences xn and yn such that mod of xn minus yn less than n and f of xn minus f of yn is greater than equals to epsilon naught. How we are getting? So this delta now choose for each n we have 1 by n neighborhood. Okay, and you have a pair of elements. So let's say that elements a pair is xn comma yn for which xn minus yn less than delta. So delta is now 1 by n, and we have f of xn minus f of yn is greater than equals to epsilon naught. Okay. So for each n you will get, so therefore we will get it will generate two sequences xn and yn. Okay, such that this inequality. Now look over here. So xn and yn both are bounded sequence. Why? They are sequences from this set AB, closed and bounded interval AB. So xn is a bounded sequence. So since xn is a bounded sequence, so what we can say? So if we have a bounded sequence, what is the property we have? Bolzano-Weierstrass theorem. So it has a convergent subsequence. Okay. So then since xn is a bounded sequence, xn has a convergent subsequence, say xRn by Bolzano-Weierstrass theorem. So let's say that subsequence converges to L, that element L. Okay. So it will has a convergent sequence that will be L. Now look over here, closed and bounded interval. This is a very important thing. because the set closed and bounded interval is a closed set, this L is also an element of the closure. Hence, A comma B is closed, L belongs to. So this is the property that Xn is a bounded sequence. We are using the property that this closed and bounded interval is a bounded set. Okay. And here we are using the property that closed and bounded interval is a closed set for which L belongs to AB. Okay. Okay. Also, mod of XRL minus YRL less than 1 by RL. By construction, XRN minus YRN less than 1 by RN. And 1 by RN converges to 0 as n tends to infinity. Fine. So all these together will imply that YRN is also converges to L. Okay. So this also implies that fine. I think I have to prove a theorem before I. Okay, up to this point. Okay, I have to use a theorem. I will prove the theorem after this thing. So we'll use it the fact. Okay, we'll use the following fact, which we will prove after this theorem. What is the fact? It says that f is continuous at a point, f is continuous at C if and only if whenever a sequence Xn converges to say f of Xn converges to f of C. Okay. We'll use this fact to prove this, that if f is a continuous function at say, if and only if we have a sequence Xn which converges to C, then f of Xn, this new sequence, is also it will going to converge to f of C. Okay, so we'll use this fact. I should have proved this before, but okay, let's continue this flow. That we'll use the following fact: f is continuous at C if and only whenever you have a sequence Xn converges to C, f of Xn converges to f of C. Okay, good. Now, L is an element of this closed and bounded interval AB, and the function f is continuous on closed and bounded interval AB. So therefore, function is continuous at L. Okay. So now if is continuous at L implies, so look over here, XRN converges to L as well as YRN converges to L, correct? So implies that f of XRN, this sequence, and f of YRN, both of these sequence converge to L. Both of these sequence will converge to L. Sorry, f of L. I don't know what is going on. Style it is. Okay. Fine. So now let's use that definition of convergence. Okay. So then there exists K belongs to set of a natural number such that f of XRN minus f of L less than epsilon naught by 2 and f of YRN minus f of L is also less than epsilon by 2 for all n greater than k. Okay. Why this is so? Because the sequence f of XRN converges to the point f of L. Okay. Therefore, for gets epsilon naught greater than 0, you will have a positive integer n for which f of XRN minus f of L will be less than epsilon naught by 2. Similarly, f of YRN converges to f of L. So therefore, you will have another positive integer for which this will also going to work. So you can always take the maximum of both of that integer. Okay. Therefore, we will have only one natural number k for which both of these two inequality will hold. Okay. So okay, epsilon, it should be epsilon naught by 2. So then what? Then thus using triangle inequality, we have f of XRN minus f of YRN, okay, less than equals to f of XRN minus f of L plus f of L minus f of YRN, which is less than epsilon naught by 2 plus epsilon naught by 2, which is equals to epsilon naught for all n greater than k. And this is a contradiction. Why? Because by construction, f of XRN minus f of YRN should be greater than equals to epsilon naught. But we reach at a point where their difference is less than epsilon naught. Okay. So which is a contradiction. Why we reach at contradiction? Because we assume that f is not uniformly continuous. So therefore, f is uniformly continuous on AB. So if you have a continuous function defined on a closed and bounded interval, then it will be uniformly continuous on closed and bounded interval. Okay. So in this proof, So instead of closed and bounded interval, can we generalize this statement theorem? It's a compact because in this proof we use the property of closed and bounded. Which are the properties we have used of closed and bounded? It is a bounded as well as it's a closed set. And we know that in a real line, a bounded closed set is nothing but a compact set. Or a compact set is closed and bounded in integral theorem. So therefore, we can say that if we have a continuous function defined on a compact set, then the function is uniformly continuous on that set. Okay. So please write that as a note. I'm not writing it. So if we have a compact set and if we have a function defined on that compact set, then it is uniformly continuous on that set. Okay. Okay. Now, as I promised, we'll prove the thing that if a function is continuous at a point, then xn converges to that point, f of xn converges to the functional value of the point. It's also called the sequential criteria, okay, of continuity. Okay, let's try to prove that. Okay, by the way, any question? Do you have any question regarding the proof?
So like you define it for 1 by x, so it goes into interval from 0 to infinity. Then it will be a uniform continuous?
No, obviously not. That's not a b and be a real number. That you are taking closed and bounded interval 0 to infinity, it's not. It's open, not only open, that's not also a real number. Infinity is not a real number. So obviously that's nothing to worry. Okay, so it's called sequential area of continuity. Let D is a subset of R, comma C belongs to D, comma and A from D to R be a function. Then F is continuous at C if and only if whenever xn, whenever we have a sequence xn converges to C f of xn converges to f of c. Fine. So what we are saying, so continuity implies if we have xn which is converges to c, is always going to imply that f of xn converges to f of c. And if this is true for all sequence xn, then f should be continuous at that point. Okay. Oh. So let's assume that f is continuous at the point C. Okay. Let f be continuous at C. Okay. So and xn converges to we are assuming that f is continuous at C, and we have a sequence xn which is convergence to C. Okay. What we have to show? We have to show that. So to show, writing in short, that f of xn converges to f of C. Okay. Let's take, so let epsilon greater than 0 be given. So we have a pre-assigned positive epsilon. Okay. Then what? By continuity, since f is continuous at C, so there will exist a delta. So then there will be a delta greater than 0 such that f of x minus f of C is less than epsilon whenever x minus C less than delta. Fine. That's the definition of continuity at the point C. Okay. And also what we have, there will exist a K also. Okay. Also, there will exist a positive integer K belongs to set of a natural number such that mod of xn minus C is less than, okay, I'm taking this is less than delta for all n greater than K. This is because of the fact that xn converges to C and we have delta positive, same delta, okay, for which xn minus C is less than delta for all n greater than or equals to K. So same delta, this delta is this. So now you can see that because xn minus C is less than delta, obviously this will imply that clearly you can see that f of xn minus f of C is less than epsilon whenever n greater than K. Why? Because you see that f of x minus f of C less than epsilon whenever x minus C is less than delta. Okay, x is an element of D. Obviously, xn's are element of D. So when x minus C is less than delta, you have fx minus f of C less than epsilon. Now xn minus C, so in place of x now you have xn. Xn minus C is less than delta. So obviously, f of xn minus f of C should be less than epsilon. Okay, so this is nothing but, so this, that means what? So this is nothing but f of xn converges to f of C. So this part is very trivial. Okay, other way. Assume that if we have a sequence xn converges to C, then it's always implied that f of xn converges to f of C. We have to prove that f is continuous at C. We'll prove by contradiction. Okay. So conversely, suppose f is not continuous at C. Suppose f is not continuous at C. So what we have to do, if we have to use the fact that if we have a sequence xn converges to L, implies that f of xn converges to f of C. So we need to get a sequence xn, correct? So we have to construct a sequence xn. How to do this? So now f is not continuous at C, we have to use this fact. So what we can conclude from this, f is not continuous at C means what? So there exists an epsilon for which you're not going to find a delta. Okay. So then there is an epsilon naught greater than 0 such that for all n belongs to natural number, what will happen? F of xn, okay, minus f of c is greater than epsilon naught, but xn minus c is less than 1 by n. So this will generate a sequence xn. Correct. Is it clear? For each epsilon, there will exist an epsilon greater than 0, such that whatever delta neighborhood you will choose, now delta neighborhood is 1 by n neighborhood. For each natural number n, we are considering 1 by n neighborhood of C, and for each neighborhood we have a point. Let's say that point is xn, because this point depends on the choice of n, and therefore f of xn minus f of c is greater than epsilon naught. Okay. Now, obviously, this inequality imply that so now mod of xn minus c less than 1 by n implies xn converges to c. It's very easy to check that this will converges to c. You can use sandwich theorem as well. Okay, if you don't want to use anything else. Okay, it's nothing but c minus 1 by n less than xn less than c plus 1 by n. Now take n tends to infinity, c plus 1 by n converges to c, c minus 1 by n converges to c. So by sandwich lemma, xn should converges to c. Okay, so this implies that xn converges to c. So now by assumption, the f of xn converges to f of c. Correct? This is our assumption that if this is the condition, we assume and we are trying to prove that f is continuous at c. So what was our condition? If we have a sequence xn converges to c, then f of xn should converges to f of c. Now we have a sequence xn converges to c. So by consideration, f of xn should converges to f of c. Now you can see that this is not so, because f of xn minus f of c will prove that this is greater than epsilon naught. Okay, because which is, but the fact xn minus f of c greater than epsilon naught for all n or concludes f of xn cannot converge to f of c. So we get a contradictory statement. So why we get the contradictory statement? Because we assume that f is not continuous at f of c. Okay, so this assumption is not tenable. So hence f is continuous. F is continuous at c. Okay. So this is another it's a very useful fact that if we have a sequence xn converges to c, then f of xn should converges to f of c if f is continuous, if and only condition. Okay. So now we'll see 1-2 example, and then we'll conclude the session. Okay. By the way, any question till now? Okay. So what we learned till now? We learned the definition of continuity. And we saw that in the definition that delta depends on not only the choice of epsilon, but also the point we are discussing. And from there we got the definition of uniform continuity. And we observed that our uniformly continuous function is continuous, but the converse is not true. But if we consider a compact set, then a continuous function on a compact set is uniformly continuous. Okay. And to prove that, we have to use the sequential criteria of continuity, and we prove the sequential criteria of uniform continuity. Now, let's take this example. F of x, let's say cos 1 by x when x not equals to 0, 0 when x equals to 0. Is it continuous at the point x equals to 0? Is it continuous at the point x equals to 0? Cos 1 by x, x not equals to 0, and 0 when x equals to 0. Why not? How to prove that it is not continuous? The point. Yeah, we'll use the sequential criteria. Good. So. Okay, so first of all, C is 0. And xn is xn equals to 1 by n. Okay. Then we have cos n, cos xn, which will be cos n. That will not going to be a good idea. So what we can 1 by n pi we can take. Correct. N pi will take xn equals to n pi. Then you can see that xn converges to 0. So if it is continuous, then f of xn should converge to f of 0. Okay. So what is f of xn? It's a cos n pi, and cos n pi is minus 1 to the power n, and obviously this is not converged at any point. In particular, cannot converge. So f is not continuous at the point. Thus, f is not continuous at x equals to 0. Okay. What about the other points? You can prove that it is continuous in all other points. Okay. Other example. Fx equals to 1 if x belongs to the set of all rational numbers. 0 if x does not belong to the set of all rational numbers. So now discuss the continuity of the function. Let's say we have a point. Let's C form the set of all rational numbers. Okay. So now we know that we're always going to have a sequence of irrational number converges to a rational point. Okay. So let Rn be a sequence of irrational such that Rn converges to C. Okay. So consider a sequence of irrational converges to C. You can easily take, like, if you have a C, take C plus 1 by or root 2 by n. Okay, so that's also going to give you a sequence of irrational number. Okay. That will converge to C. Now, what about f of Rn? F of Rn, which is nothing but 0, and it cannot converge to 0 converges to 0, which is not equals to 1, which is f of C, because C is a rational number. So this means that f is not continuous at the point C, because C is was arbitrary. So function is not continuous at any rational point. Okay. Thus, f is not continuous at C. What about C is an irrational number? We will consider a sequence of rational which will converge to that point, and you will have the similar type of thing. So this is an example of a function which is nowhere continuous. Okay. So in fact, f is nowhere continuous. Okay, that's all from my side. Any question from you? Okay, we'll discuss many other things. Okay, one important. Okay, before I conclude the session, we're not going to prove many other theorem like algebra of continuous function, because that's very easy sometimes and lengthy some cases. Like if we have a function f which is continuous at C, another function g which is continuous at C, then sum of two continuous function is continuous, product of two continuous function is continuous, and also the f by g is well defined, and then it's also going to be continuous at that point. Okay, and if you multiply a function by a constant, this is also going to be continuous. Okay, in the book, in the most books, you will find that they use the epsilon delta definition, but you can use this fact as well. Let's say it is f and g both are continuous at C. Okay, so let's say we have a sequence xn converges to C. Then what will happen? F of xn converges to f of C, and g of xn converges to g of C. Use this fact: f of f plus g of xn is f of xn plus g of xn. It will converge to f of C plus g of C, which is f plus g of C. Use sequential definition. You can prove that. You can prove this type of thing very easily. Okay, without using epsilon delta definition. So sequential criteria is very much helpful. Okay. The next class we will try to find. So we saw that a continuous function maps a convergent sequence to a convergent sequence. What about Cauchy sequence? So does a continuous function map a Cauchy sequence to a Cauchy sequence? Okay, we'll see that. Okay, next class we'll start discussing, but before that we have to prove a little theorem. And okay, we'll again meet tutorial, so we'll solve some problems there as well. Okay, any question from the online participant? Any question from online? No question.